introducing the moderator of the panel, which is Ulrike Tilmann. Ulrike is a mathematician who is known for her pioneering work on moduli spaces that has been motivated by problems in quantum physics and string theory. Some of her recent work is on the challenges that are motivated by data science. So you see there is some links also to topics that are important nowadays in computer science quite heavily. Ulrike has received numerous awards, the Whitehead Prize, the Bessel Forschungspreis. She is an elected inaugural fellow of the American Mathematical Society, the Alan Turing Institute, fellow of the Royal Society, and a member of the National Academy of Germany, Leopoldina. Currently, she is the Rothschild and Son Professor and Director of the Isaac Newton Institute in Cambridge. Ulrike, please take over from here.
Thank you very much. Well, thank you very much, Holger. I want to really just briefly introduce this new session. So I think it's a new session for the Heidelberg Forum, the Kaleidoscope of Mathematics and Computer Science. There are so many different facets in both of these subjects that we want to bring out. And really, we start just like the Sparks session, really, with three proponents who will give us a glimpse in their research. And afterwards, we will have a conversation about the pathways and interests. So it's my real great pleasure to introduce Alicia Dickenstein. Alicia is a professor emeritus in the University of Buenos Aires and a senior research fellow of the CONICET, which is the National Research Council in Argentina. She has had many prizes. Let me just concentrate on a couple of them. One is the 2015 TWAS Prize in Mathematics. TWAS is the World Academy of Sciences. She has had the 2021 L'Oreal UNESCO Prize for Women in Science, and the Lefschetz Medal for given out by the Mathematical Council of the Americas and just this year. In particular, I want to emphasize her many roles in mathematics. She has taken her role as a leader in mathematics also serious to take the responsibility for the community. And one is that she was the vice president of the International Mathematical Union, which of course is one of the prize givers. So with that, I would like to invite Alicia to the podium.
Happy to be here. So let me tell you a little bit about my mathematical path in 10 slides. So in fact, it was not a path. I will tell you later about the difficulties I had to get here. So according to MathSciNet, I work on all these areas, and I did. This is not chronological, but then you will understand how I was switching from one to the other, was left alone in Argentina, and I had to find my path. In fact, I started with several complex variables, and then I moved through these other subjects. And I will tell you a little bit what I'm doing now. So one of the leading subjects of my, let's say, last 20 years' work is studying discriminants. So a basic discriminant we all know from school. It's a discriminant of the second degree equation. And discriminant in this case is that you take the polynomial ax squared plus bx plus c. This is a polynomial in the coefficients of the given polynomial. So we have eliminated the variable x. And it will vanish whenever there is a double root. So it will vanish on the red curve because then it is tangent to the x-axis, and not on the green curve. But there are also discriminants associated to polynomials of any degree in one variable, and also in the multivariate case. For instance, if we take a polynomial of degree 3, like this one, ax cubed plus bx squared plus cx plus d, The discriminant is this polynomial of degree 4, and it has a beautiful combinatorial information that was mostly found by Gelf and Kapranov and Selevinsky, and then followed up by many people. It will vanish whenever there is a double or triple root, which a root which is not simple, where f and the f prime vanish together. So we have this family of curves there, the green, the middle one, the red, and the blue. And so we move it, and the discriminant will vanish on the red curve. Well, in this case, it is tangent, and you see that the green curve has only this polynomial. Is the graph of polynomial with a single real root, and the blue one has 3. So to move from 1 to 3, we need to cross the discriminant, right? And maybe I wrote this with A equals 1 and B equals 0. In this case, in number theory, in general, these are called P and Q, and this is maybe the discriminant that you are more common to see. Okay, so what is here, we have a surface in 3 space, and there is a parameter which is moving from the first picture, to the first picture to the other one. If I go here back, can I make it again? Yeah. So we would like to trace and see exactly when is it that we get this singularity. Even if I haven't defined singularity, you decide it's obvious to think that there is a singularity in the last picture, right? Okay, so what are discriminants used for? For instance, they can use, they're basic in our vision. When we look at an object, what we see is the contour, is where the lines from our eyes touch in a tangent way the object. They are only used to understand the things that you have to avoid when moving a robot. This is a parallel robot used for medicine, for surgery, or the other one is a flight simulator. You don't want this to explode, or you don't want to have more movements that are expected. You don't want the surgery platform to move. And then you also need to, these points that you need, these singularities you need to avoid, I described by our discriminants. So just don't read what is in there, just let me show you the picture. So here, in this case, we have a family of 2 polynomials in 2 variables. So one is x to the 6 plus a times y cubed minus y, and the other one is y to the 6 plus bx cubed plus minus x. So there are only 2 parameters, a and b. And then we see that we are trying to find out how many positive roots can we find when we move a and b. Okay? The other pictures there are in the a-b plane. And the picture, what you see there, this is discriminant equal to 0. And it had already been proved that you could have up to 5 positive solutions. But you do anything naive, you will not, so, and the number of real roots is the same in each of the chambers in the complement of the discriminant. But I see that my time is running, I didn't realize. So I will run. So what happens is that you see, if you need to amplify 1,700 times to find this tiny, tiny, tiny red region where there are 5 positive roots, it's very unlikely that if you do any probabilistic thing, you will find them. But we are trying to find them, to assert how many and be able to find them. I don't know how AI can do this task, at least for now. So also discriminants are used in hypergeometric functions. In fact, I use them there. They describe the singularities. And they are also used in the study of biochemical reaction networks, because it's important to decide on how many positive solutions the system has. What do I mean? So I've been working with using algebra and geometry in different signaling pathways in the cell. And see, these are just pictures, cartoons of different mechanisms. One is the famous ERK pathway. So in general, this is modeling using what's called mass action kinetics that go to Norwegians in the 19th century. So that you get a system of ordinary differential equations, and f of x are polynomials. So if you look for the steady state that drive the dynamics, then you need to find the positive point of an algebraic variety. And also there are some natural conservation laws. And then what we were able to do here is to describe that in many or most of these systems, there was an underlying structure that we called a messy structure, not because of Leo Messi, but maybe we were very close to this. This was before the World Championship. And then what's interesting, so looking at this structure, we were able to prove theorems for quite different mechanisms, okay, without any needing of any need of any simulation. And then let me just show you some of my current interests. So in these are just some survey short articles where you can read about how we are using algebra and geometry in systems biology. This is in the notices of the AMS, the other is in SciAm News. This was last year. These articles are mostly on this area on the left, on this area of applications to systems biology. But in fact, the other one is a different topic. We try to extend the Boolean case. In some cases, instead of having a continuous value, we have just like a gene is on or off. But then having on or off is not many times enough to describe the behavior. So maybe you want it on, off, or half on, and then it can have a different behavior. So we try to deduce elements of multi-valued logic, and together with counting lattice points in polytopes, this is going to appear in a science journal on applied dynamical systems, and then this is something like that with a student, and there is a small advertisement. So I edited, I was the chair of I don't program, but there was an International Congress of Mathematical Software. This happened in 2024. But there will be another one in 2026 in Waterloo, just before the ICM. And this is, you can go there and you can propose a session. And if you propose a session, you're automatically part of the program committee. And you have to take responsibilities on your own. And then also this is part of things still related to algebraic geometry that I am working on. This is not related on discriminants, residues, and obstructions in compact toric varieties. And this article is with Ragni Pini, who is somewhere there. And just let me end with this. You need math to draw this beautiful heart. Thank you very much.
Thank you very much, Alicia, for a beautiful talk. It's amazing how classical mathematics, like the discriminant, has applications in so many different forms, and even today. So let me introduce our next speaker. That's Corinna Ulcigrai. Corinna is, well, she's Italian, but her academic pass letter to Princeton and via Pisa and Bristol in the UK, and she's now at the University of Zurich in Switzerland. Among many of our accolades is the one that I really want to point out is namely the prize of the European Mathematical Society. It's a little bit like the Fields Medal, only you have to be even younger in order to get it. So Corinna got this prize a few years ago. She also got the Whitehead Prize and the Brin Prize for dynamical systems, and was a speaker at the ICM last time around. It's my great pleasure to ask Corinna to come to the podium and tell us about her subject, which includes chaos, including slow chaos, whatever that is. So please.
Thank you, Ulrike. Hi, everybody. So I'll try to give you a glimpse into my research, and I chose to do so by presenting 3 key words: slow chaos, polygonal billiards, and renormalization. So it will be a brief tour of these 3 concepts. So let's start with slow chaos. And let's start with chaos. So I think many of you might have heard of the butterfly effect. So let's try. Who has heard of the butterfly effect? Yeah, almost everybody. It's a very popularized feature of chaos, and specifically of deterministic chaos. So we have a system which is completely deterministic, described by rules by a mathematical model, by equations. But still, it can be very hard to predict. And Edward Laureates, who was a mathematician and meteorologist, popularized this image of a butterfly in Brazil creating a tornado in Texas. And this image gives the idea that, for example, weather is hard to predict because even though we have a deterministic model, it has a sensitive dependence on initial conditions. So if I change a bit to the initial state, it can have a very different future evolution. And by the way, there is a computer aspect, forgotten part of this story. It was not really Edward himself who discovered the butterfly effect through simulations of the weather, but there are two hidden heroines of chaos. There's a nice article on Quantum magazine, but I also recently discovered that two early-day computer scientists, Margaret Hamilton and Ellen Fetter at MIT, were running the weather simulations for Lawrence with one of the early days computers. And then Hamilton went on to NASA and wrote the code for the Apollo mission. Ellen Fetter got married, had children, and when she wanted to come back, she couldn't program anymore. There were not so many young women then. Okay, so this is chaos. The butterfly effect is a feature of chaos. What's the difference between fast and slow chaos? So fast and slow, very, very roughly, refers to the speed of the butterfly effect. So if two initial conditions diverge quickly, quickly means exponentially in time, we talk of fast chaos. If the divergence is slow, slow means sub-exponential, for example, polynomial in time, then we call the system slowly chaotic. Another characterization is through complexity. So maybe many of you have heard about entropy. And fast chaos has positive entropy, so it's rich in complexity. While slow chaos have systems that do have the butterfly effect, but they are low in complexity. So the entropy is actually zero. Again, all my research has slow chaos as an umbrella. So I've studied through various aspects, various subjects, ergodic theory, probability, mathematical physics, geometry. I've studied a lot of systems which are slowly chaotic. Actually, a key example of slow chaos comes from surfaces. And a lot of my research has to do with the chaotic properties, fine chaotic properties of flows on surfaces, which are area preserving. But I will not tell you about that. I'll tell you a little bit about polygonal billiards. It's more playful for this talk. And let me mention, there is a symbolic aspect. So all these systems, flows on surfaces, polygonal billiards, can be coded, can be encoded through sequences. It's called symbolic coding in dynamics. And the sequences that describe low chaotic, slow chaotic systems have low complexity, not surprisingly, and they are also interested from the combinatorial point of view. Okay, so word number 2, polygonal billiards. So billiards, mathematical billiards, are an idealized version of the billiard game. So you know that if you shoot a ball in a billiard, it bounces on the wall, making equal angles before or after hitting the table. In the idealized version of a billiard, the ball has no mass, it's a point, there is no friction, and we don't have pockets. So the ball never hits a pocket, and it will keep moving forever. So we are interested in infinite trajectories, and we change the billiard table. There are many types of billiard tables with obstacles, with curved walls, and so on. And I can show you the slow chaos, the butterfly effect in a billiard visually. So here I have 2 simulations. And in the first one, there is an obstacle, which is a circle. So let me do this again. So what am I doing? I'm going to shoot balls which are parallel, so same direction, but slightly different initial position. And as you see, they immediately are scattered by the convex obstacle, and very quickly they can be anywhere in the billiard. So you see the butterfly effect. They start close, and they immediately, very quickly scattered. Here, the second has a rectangular obstacle. So let's do it again. They don't immediately separate, but if some hit the corner, some don't, then they are in different parts. So you can see that there is a butterfly effect. The corner of the rectangle will diversify the evolution, but it's much slower. So intuitively, this is slow chaos versus fast chaos. And I can also show you what I mean by encoding symbolically these systems. So through a clip of a movie made by Ophir David, who was a postdoc at the time in my research group. So what is the music of the square? Let me show you. Sound. Can we have the sound from the, I don't know, let me try it again. So here I'm just encoding the billiard ball through the sequence of sides that it hits. So it's actually, you can do it with a symbolic sequence. You can do it through colors. Those are the colors of the sides that were hit. Or you can do it through music, so associating a tone to each side. And let me also show you the music of the octagon. Okay, so music is just a playful way to show you. You can try to ask yourself, what are these patterns? Why do they sound nice? And what are all the musical patterns that a billiard in a polygon can produce? So in the case of the square, these are very well-known sequences. So they are related to so-called Sturmian sequences, which are actually the lowest complexity non-periodic sequences in 2 letters. So, and the relation between the square and Sturmian sequences is very nicely explained by Caroline Series. There's a beautiful article, UK mathematician, now emeritus, then young. And in other polygons, regular polygons and semi-regular polygons, characterizing the musical patterns or the through an efficient way to produce them, it's something that I've done together with John Smiley, and in the semi-regular case with 2 young women, Irene Pasquinelli and Diana Davis. That you see all 3 of us in the picture. And what about other billiards? Billiards are important in physics. So here in these animations, you see 2 very famous billiards in physics, known as Lorentz gas to the left and RFS model to the right. So both of them were models in the early 1900s, introduced to study features in statistical mechanics. And let me run it again. As you see, they are infinite billiards, where the ball, the ball bounces around a periodic array of scatterers. Around, in the Lorentz gas, it could be atoms on a metal, regularly spaced, and rectangles in the RFS variation. So a question in physics is, will the typical billiard trajectory explore all parts of space? Or, more formally, is the billiard ergodic? And in the case of the Lorentz gas, in the already 70s, there was a lot of research, mathematical rigorous research. And in the Lorentz gas, when the circles are scatterers around, the answer is yes. A typical billiard ball will visit all of the space. In the case of the RFS model, it's harder to understand and it's harder to simulate because of slow chaos. And what I proved a few years ago with a Polish author, just to front check, is that no, in the RFS, if you shoot at random a ball, it will not go everywhere. There are, for example, here you can see a part of space which will not be visited. And there are actually some trapping regions. So we proved that there are trapping regions, but actually this picture, it's a picture by Yuri Tumarkin, who is a PhD student in my group. And Yuri has proven mathematically, he gave a geometric description of the trapping regions, which have a very complicated structure. So here I'm zooming out on the trapping region, and you see it has very fine structure. And this leads me to the last word, renormalization. So the structure that we saw has a lot of self-similarity. And also the patterns, the music that we heard, has a lot of self-similarity or quasi-periodicity. So it sounds nice to us because there is regularity hidden. So when you have structures, shapes like fractals, sequences like the music of the octagon, or functions that have sort of multi-scale structure, they have different scales, and each scale has a similar structure, maybe the same if it's self-similar, or a similar shape if it's approximately self-similar, then you can use the idea of magnifying different scales. And this can be done through renormalization. So I have only this is the almost last slide, so I will not tell you what renormalization is for me. It means something to physicists. It means something else in dynamical systems. I forgot to say, we have, if you want to know more about billiards, Sergei Tabachnikov should be in the audience. Yes, here he is. He actually read many of the applications of the mathematician here. He's in the organizing committee of the forum, and he's written a beautiful book about mathematical billiards, accessible to undergraduates. And one of the laureates here, Dennis Sullivan. Dennis Sullivan is here in the audience. Well, he is around. And he's one of the seminal work on renormalization in dynamics has been done by Sullivan. And in my setting of billiards and polygonal billiards and flows on surfaces, the renormalization that I use is related to rescaling time and rescaling trajectories and changing geometry of a surface. And the last slide, the real mathematical tools come from an area called Teichmüller dynamics, where you work on the moduli space of surfaces and you deform the geometry. And a lot of laureates, a lot of Fields medalists, Breakthrough Prize winner Alex Eskin, and have worked on this area, Yokoz, Avila, Kosiewicz, McMullen. And I want to remember Maria Mirzakhani, who I think is the first woman who got the Fields medal. She was a great inspiration for me. I was a PhD student in Princeton when she was an assistant professor there. And maybe, as you know, she passed away at the age of 40. So I think it would have been great to have had her in one of these forums. But so their mathematics, some of their mathematics goes into the proof, for example, of the Aerofest model. Thanks a lot.
Thank you. Beautiful lecture, and really lovely to see all this order in chaos. So I come to our last speaker this morning, Rob Tarjan. He's an American computer scientist and mathematician, and I really like the combination. Mathematics has always been at the root of all these new sciences that come up, including computer science, of course. And he has used, in particular, graph theory to come up with interesting algorithms, including he was the co-inventor of both the splay trees and the Fibonacci heaps. So I'd like to invite Rob to the stage. But I should not neglect to also mention his fantastic prizes and achievements. He is the first recipient of the now called Abacus Prize, and he received that all the way back in 1982. He also received more recently the ACM Turing Award, and with Hopkroff, who is I think also in the audience, for the fundamental achievements of the design and analysis of algorithms in data structure. So please, Rob, please.
Thank you, thank you. Yes, I got the Turing Award a little more recently. That was 1986. So I would like to do two things in my presentation here. First, I wanted offer some philosophical remarks about computer science and my view of research and what I do, which is theoretical analysis of data structures and graph algorithms. And then I'll very quickly mention a recent collaborative result of mine. So let's start out with some observations. What I do is mathematics, but in the computer science space. And unlike mathematics, computer science is a very young discipline. It's only been around for maybe 80 years if we're generous. And as a result, it's a problem-rich space. We have seized upon the low-hanging fruit, but left many things not completely understood. Furthermore, as computers get faster and faster, memories get bigger and bigger, the design space for designing algorithms only gets richer and richer. So the obvious conclusion, I think, is let us explore the design space systematically, maybe revisit some classical problems and try to understand them much more fully. Let me say something about theory versus practice. How do we measure efficiency? If we want to make progress theoretically, we have to make simplifications. So the simplification we made 40 or 50 years ago was to study worst case running time of a sequential algorithm as a function of the input size or of some parameters, ignoring constant factors. And this abstraction turned out to be very useful because it separated out sort of the essence of the problem versus complicating factors that were not so relevant. And so over 50 years, we've seen much theoretical work on algorithms that has resulted in beautiful, theoretically efficient, but I would say more and more complicated and impractical algorithms. And the conferences in my field, Stock and Fox, there seems to be value placed in complexity for complexity's sake, which I think is not necessarily ideal. So my goal developed over time is, we can think of it as elegance, quality of being pleasingly ingenious and simple. The goal is to obtain, identify, discover the simplest possible efficient methods to solve basic problems. Paul Erdős, who was a well-known mathematician, had this concept of proofs from the book. That's the book in the sky. That's what we want to do in the algorithms space. That's my goal. Provable, good algorithms, simple algorithms that people actually use in practice with provable resource bounds for important input classes, efficient in practice. The analysis can be deep, but the algorithm has to be simple. All right. And it's very important to choose the right problem. Choosing the problem is more important than the solution often. So let me give you quickly a recent example. This is joint work that I did with Bernard Heupler, who was a master's student at Princeton, who I ran into again a decade later and started working with him and his colleagues to prove optimality of Dijkstra's algorithm in a very strong sense. So Dijkstra's algorithm, we remember, is a very simple algorithm that uses the greedy method to find shortest path from a vertex in a given graph. Think of network road planning. You want to get from point A to point B, minimizing your travel time or the distance or some other function. So the strategy is expand out greedily. At each step, discover the next closest point to the goal vertex and add that to your set of vertices for which you know the shortest distance, and then go one more step at a time. That's Dijkstra's algorithm. The question is, how do you implement that efficiently, and can you prove that it's optimal in some sense? Now, Dijkstra's algorithm actually does more. First of all, it computes the shortest path from the start vertex to every other possible vertex, but it does it in a particular order. It computes the vertices in order by distance from the source. So it has this stronger property. So that's what we wanted to study. How much time does it take, or how many comparisons of combination of edge weights does it take to find the distances to all the vertices in increasing order? Now, Dijkstra's original algorithm, as he implemented it, ran in quadratic time in the number of vertices, which is completely impractical for large graphs. If you use a data structure, some kind of heap or priority queue, and plug it in, then you can reduce the running time to something like the number of edges in the graph times a log overhead for the data structure. Back in the mid-1960s, Mike Fredman and I invented this data structure that we call the Fibonacci heap, which reduced the running time to linear in the number of edges plus a log overhead n log n, where n is the number of vertices. So in some sense, that's optimal. But what happens if you have a particular graph? So let's suppose we have a particular graph, and the variability is the weights of the edges. Can we then say something about Dijkstra's algorithm and prove that it's the most efficient possible way in terms of counting comparisons to within a constant factor to produce the result? So we proved this. If you tweak the algorithm in a couple of ways, we had to invent a variant of the Fibonacci heap to get this to work. This was published last year in the Foundations of Computer Science conference and actually got a Best Paper award for this. So that's the result. We threw 2 new ideas in and were able to prove this nice result. Now, is this the right answer? Well, first of all, there's another problem that's related to sorting. If I want to sort a set of numbers, and I'm given some pre-existing information, I'm told that certain pairs of numbers have a certain relationship. So the 10th one is less than the 25th one, and so on and so forth. Suppose I want to sort using the pre-existing information in an optimal way. Turns out the ideas we used in this optimality of Dijkstra's algorithm result gave us a simple and optimal algorithm for that problem as well. So that was nice. But let's go back to this question of optimality of Dijkstra's algorithm. What I said is that the algorithm is optimal if we require that the algorithm produce the vertices in increasing distance order. But if I'm only interested in a particular goal vertex, I don't have to produce things in distance order. So if I relax the requirement, in fact, Dijkstra's algorithm is not optimal. And there's recent beautiful work, which was in Stock 2025, again, the Best Paper Award, which gives a better time bound for the problem where we don't require sorting the vertices by distance order. Now, I would say this algorithm is complicated, and it's not going to be useful in practice, but it's a beautiful theoretical result. So let me stop there, and now we'll have our panel discussion. Thank you.
Thank you very much. Indeed, we now have our panel. We'll start with a conversation, but we hope to have some time also for audience questions. So all the questions you have in your mind right now from the talks, keep them in your mind, but also maybe some more will come up. So thank you. I'll start with our first question. Maybe I start with you, Alicia. What sparked your interest in the first place to become a mathematician, to go down the route you took?
Well, I had no idea that one could be a mathematician, that such a career existed. And I was planning to study education. I enjoyed math, but I had no idea this could be my life. And then they offered a vocational test. And it happened, I was so lucky, that the woman offering the test, she was a philosopher, pedagogist, I don't know, something different. But she had designed this, and one of the tests was about, logical thinking. And she said, you have to study math. And I said, math? What kind of strange people I'm going to find there? I said, no. I said, I am a frustrated mathematician. You go and start with math. And then I went and immediately realized they were my kind of strange people.
That's great. Yeah, Corinna.
I had no idea that I would become a mathematician because I had no idea what mathematics was about when I had no example of a person who no. So yeah, so I thought I will become a writer and write books, children books. That's what I thought when I was young. But although thinking about it later, I did enjoy solving these logic riddles and these quizzes on, I don't know, magazines. So later, I was good in all subjects. I was good in mathematics in school, but I didn't like the mathematics in school. I thought it was boring and mechanical. So it was only later I took part in the mathematics Olympiads, not in the international ones, only in the Italian math Olympiads. But there I discovered that actually math can be creative and can be problem solving. And that's where I discovered that I liked it. That's what I wanted to do. And yeah.
Great. Actually, hands up who has taken part either in the mathematics or I think there's a computer science Olympic as well. Only two? Can't be. There must be more. No? Okay. Shy. Okay.
I read a lot of science fiction as a kid. I wanted to be the first person on Mars. That's actually still a possible goal. But I discovered I had a fear of heights, so that went away. I got interested in Martin Gardner's mathematical games column. I like to play mathematical games. When I was in the 8th grade, I had an amazing math teacher, Mr. Wall. This is a public high school in Southern California. He taught us piano's axioms. This was before the rise and fall of the new math. It was wonderful for some of us, so I got excited about mathematics at that point. I had opportunities in high school to program on some very primitive machines. Bendix G15, if anyone remembers that one. So I got interested in the four-color problem. So I was interested in graph theory, computation. I got an undergraduate degree in math at Caltech, and when I was deciding on grad school, I applied both to computer science departments and to math departments. I figured I could do mathematics of a concrete kind where you can actually run your algorithms and see them work. So I went into computer science, and I've never regretted that decision.
So I have to ask, because we heard before, when did you do your first programming? How old were you?
Well, I actually programmed on you couldn't call it a computer, it was an IBM calculator, and you programmed it by plugging wires into a board. The Bendix G15 I was programming in high school, actually.
Right, okay, on the calculator, great. So you're obviously very successful, but I think we have a young audience, and it's always interesting to look backwards. And I'd be interested to hear what you think the obstacles were that were thrown one way or another into your pathway, and how do you overcome them? Really, shall we start with Alicia?
So I would like to concentrate on this, hoping that this could be useful for young people here. Anyhow, yesterday, this 2-minute poster presentation were amazing, and maybe they don't need any of these stories, but let me tell you what happened to me. So I've always lived in Argentina. My PhD advisor had just come back with a Guggenheim Fellowship. He was very bright. There was a group. And I started working there. And then I had no idea what mathematics was, as I told you. I got married very young. I had my daughter halfway to my PhD. And then after that, I just got my son. And 1 month after that, he died of a sudden cancer. Okay? He was 45. And then we were in the middle of nowhere. The group dissolved. We were really, Buenos Aires is really, really far south. So it's maybe 13 hours from Frankfurt, 9 hours from Miami. It's really far south. And then there was, I am old, so there was not even email. There were no visitors, no one knowing more. The tradition of Argentina is analysis, Calderon and this kind of people. And then, I had the salaries were very low. I had the 2 children. I had no idea what to do. So I used to, luckily, to work with a friend of mine at that moment. But for us, I had been a good student, so you would pose me a problem, maybe I could solve it. But then I didn't know as an orphan how to pose my own problems. For us, the problems were either impossible or trivial. One of the things that I need to learn is that there's full of problems and you can find them quite easily. But this was one of the things was difficult for me to learn. So it took me like maybe at least 6 years to try to find my path. So it really took me a long time. And one of the things that happened, so just 4 years after what I'm telling you, I was invited to a 6-week college on Riemann surfaces at the ICTP in Trieste. And I was following these courses. I know it was a family effort. My children were not so small, but I went there. And then one day I remember I was in this fantastic Buren auditorium, and I think, because I felt in Argentina that I could not be productive. I saw other colleagues doing things, and I couldn't do anything. So I felt I am stupid, maybe. And then I was there, and I realized that I was getting a lot of information there, that maybe if I had this information, I could be productive. So the rest of my mathematical life was a fight for information. But it was good that I could isolate the problem. It was not my question. My problem was I was missing this important input. And then I would like to tell you a second anecdote. So the people who organized this college at ICTP, then one of them was from Mexico, and they organized a workshop on algebraic geometry. But essentially, they were just trying to get people from Latin America and working more or less similar questions. So they offered me to give a lecture, but I have nothing new to tell. So I offered to give a mini course. Okay, come and give a mini course. But this started on January 3rd or 2nd, and in Argentina. So this is beginning of summer. So this is the end of the year. Is the end of the year. This is summer, and my family also is a great gathering on December 31st. But I had to fly. The only possible flight was flying over New Year's Eve. So I was in the plane with my family behind, and there was 1 a.m. several times along the way because we were flying west. And then they gave us champagne, I don't know, and then everyone went to sleep. And I went on working on my notes for the mini course with this small light. And I was there and thinking, will I ever be rewarded? Because I thought it was a lot of effort. Now, having left my family, having there. 2 years after that, I received a letter from Dolbeau, who was a famous professor in France, saying, "Chère Madame Dickenstein, me and several mathematicians from Europe, we are interested in your work. Would you like to be a professor in Paris for a month?" So what is this? How did that happen? And then I could reconstruct what had happened. So they asked me to send notes to the bulletin of the Mexican-Brazilian Society of my notes. That was the beginning of tech. So you had to print out everything in order to be able to correct. So I somehow learned. There was a secretary at that moment helping. So I wrote my notes. And then they sent these notes for refereeing to Bo Bernson. He was a well-known mathematician in Gothenburg. And he had a Mexican wife. He had some ties with Mexico. And he did what you should do because he went to Paris and he gave to Dolbeau a copy of my notes that he had been refereeing. And so I was being invited to Paris because of these notes that I was writing on the plane at 1 a.m. on the 1st of January. So for me, yes, I am being rewarded. And the rest of my life, I said, no matter how much I work, I know that eventually I will be rewarded. And this was a leitmotif for me.
That's great. I mean, it sounds that you're already answering my second question. What made you successful is actually really persevering and just moving on. Exactly. Yeah. Okay. Corinna, would you like to give us your...
a special story, but I think the struggles that can identify throughout my careers are maybe something that are in everyday, in everyone's history as a mathematician. I think there are some moments which are difficult, and I think somehow there is a danger in you coming here and meeting the laureate, or meeting. We all think that all the laureate, or maybe us, I don't know, are like, oh, they are fantastic, they are so good. But actually, we are all, I think I can also include the laureate, we are all normal people, and we have our own weaknesses, we have our own difficult moments. So I think it's, I don't know, so okay, in my own life, I think the hardest moments were maybe when I was a PhD student, like many of you in the audience, and maybe later when I had my children. I have 2 boys, and the maternity was a difficult adjustment phase. So a good phase at the end, but a difficult transition. And as a PhD student, now, first of all, as an undergraduate, I was in Scuola Normale in Pisa, which is a fantastic place, and I learned a lot. It was wonderful, but it was also tough on confidence, because suddenly, maybe it happens, you find yourself surrounded by people who are so brilliant, so you start questioning, okay, so am I good enough? Am I really, the people are so good, am I also gonna do something? And then later in Princeton, okay, maybe it's a struggle that I think not every, but many PhD students have, and you start asking yourself, okay, but here I am, I'm doing mathematics, I'm trying to solve this problem, trying to make progress, and you also question yourself on, will I be able to, will I, and yeah, so I think it's confidence was a big issue for me. So it's kind of at many phases of my life, I was kind of dragged back, or kind of scared or worried, and created a lot of, but okay. I think talking about it and having a support network and finding people with whom you can share this, I think they're common struggles that most of us have, but most of us don't talk about it. And then you see the famous professor, you see the very smart PhD student, you see, and you think that they are so good. Or you go to a conference and everybody seems so bright, but you don't see what they feel behind the doors. So,
I imagine that, especially going to the Scuola Normale, that you met with the best from the whole country, and I see that also in being a tutor in Oxford. People come from all over, and suddenly they're among their peers, and they might not be the best, and they might know something very well, but some other things they don't know at all, and it's quite a harsh thing to learn how to deal with that situation. And you feel like your peers, you had support also from your teachers, or?
Actually, I don't know, for example, in Princeton, I think we found a small group actually of female mathematicians. There were not so many women PhD students, but there were a small group, and you kind of create maybe a friendship, a support network, people my age, or maybe slightly older PhD postdocs, and with whom you can share your fears, so you have kind of a safe space where you can, then you realize that actually, it's not only me, I'm not alone. Actually, everybody has this, not everybody, maybe someone doesn't, but many people have the same struggles, sometimes,
Well, but I don't want to impose on you, but is that at all something you relate to, or maybe your past was rather different?
I'm human just like everybody else.
No,
and
really.
I mean, I get accused of intimidating my students, but I try not to do that. But I would say, the biggest personal challenge I had was actually going from high school to Caltech as a freshman, being the star in high school, and you're thrown in, and everybody's a star. And what saved me was the first year was pass-fail at Caltech. So I could figure out how to study, how to get ahead of the game. And by my sophomore year, I understood what was needed. And I would say there are challenges to be overcome. What we do is very hard. If you don't love the subject, if you don't love what you're doing, you're probably not going to succeed. You have to be willing to work really hard, fail often, and eventually, if you're working on an important problem, you're going to fail many times, and it's going to take a long time. My PhD thesis was on efficient algorithm for planarity testing. It took me a couple of years to figure out this algorithm. I worked on analysis of disjoint set union. That took a couple of years. I have problems that I've been working on for many years that I still haven't solved. I think perseverance and love of what you're doing is extremely important. So I'll leave it at that.
So answering my second question once again, that what made you successful? Do you think perseverance is one of the main ingredients, I guess, and loving what you're doing?
If you let me follow up, another one is being open with your ideas. This is a community activity, and one of the beautiful things about it is the opportunity to collaborate with many people. And I would never have gotten as far in my career as I did without amazing collaborators, starting with John Hopcroft, but there were many more, my students and my former colleagues. So if one is open with one's ideas and one is willing to engage in collaboration, not only is it a whole lot more fun, but you learn a lot more and you get a lot farther.
I want to follow up on this community idea, because I think yesterday one of the laureates also talked about, in particular, what is humanist collaboration and how we can do that. It's an interesting thing. I think I very much feel, mathematics, computing, science in general is a community thing. But yet, how does that relate to the laureate? I mean, it's clearly also that we have some stars and some sparks. How, especially as a laureate, you feel is this combining in some things? What is that relationship?
There are many more accomplished people than there are awards. So I view these awards as recognition of the importance of the field. And I try to collaborate with everybody as equals. To change the subject slightly, why am I a professor as opposed to being in industry? I spent part-time in industry over many years, but I went to Bell Labs on sabbatical, which was an amazing place when there were the great industrial research labs. But the first year, I was starting to lose my motivation to do research. So I started teaching part-time at NYU, and I discovered that for me, it's not just the research, it's the interaction with the students. The best way to learn something is to teach it to somebody and to try to communicate. So it's not just the research itself, but it's the training process and the interaction with students. That's another part of the collaboration and the community.
I completely agree, and I do like your answer also about the openness to new ideas and possibly industry working and so on. So I think that's a very strong thing as well. But looking back at your careers, is there something you would have done different? Is there something you feel, any of you feel you might have done something that, might have changed something? A butterfly effect? I think there are probably many butterflies effects in order to get to where we are, but...
Might seem pretentious, but I would not change anything. So even the bad times, I learned things, and I was stuck there, not knowing what to do with my profession, but I had time to take care of my children at that moment, and I don't know. So I think I'm happy with my choices. I'm loving what I do, and it's okay.
I think the past, there are random coincidences. I think it had a good outcome. But I think throughout the way, I think if I could tell something to myself back then, is indeed, do not worry so much, because I think I lived some periods of my life with a lot of stress or anxiety, and I wish I could go back. And now I see, for example, the PhD students and say, this is like the best time. You have a lot of time to think about your problem. You can connect with others, and don't be. So, I don't know. So just enjoy the moment. I think I think it's a thing that maybe you gain with perspective and with confidence. So I saw somewhere a diagram where yeah, confidence in men is kind of stable, but confidence in women really grows over 40. So I think it's a bit a long time, but in my case, I'm above. So it feels maybe living better every moment. So maybe enjoy and have fun, and yeah.
It seems to be the best recipe for success anyway, to enjoy it. And
Yeah, sure, I did enjoy it.
Following up on enjoyment, I think it's important, since things are so hard and you fail all the time, you have to have a few different problems to think about, but more importantly, you have to go away and do nothing. Have some recreational activity to take your mind off everything. But in terms of what I regret, I probably shouldn't say this, but I think there's a beautiful book to be written about data structures and algorithms, a book I've always wanted to write. We'll see if something happens yet.
Something I want to relate on this failure and perseverance. I think really resilience is an important quality in research in life. And I think also we sometimes run some mentoring sessions for our young researchers in Zurich, and we have one about what to do when your research is stuck. And the first thing that we had among panelists, Fields medalist, I can say, I think, colleague Art Raviland, the Fields medalist, also saying, yeah, it's normal. Being stuck is almost all the time, and it's true at every level. It's true for PhD student to laureate, and just normalizing it and knowing that this is having fun even in failure is success. Sometimes the growth of learning is... Actually, I watched the interview. You can all watch it from the YouTube channel of the Laureate Forum last year. So Yael, who was the prize winner of the in computer science, she says she's a mathematician in disguise, and she has a long interview, 45 minutes. And around minute 39, 40, she talks about being stuck for years and years, and he says, no, this is progress. You understand what doesn't work, you understand, and you should be able to enjoy the being stuck part and not only wait for this good moment where you find...
I suppose we all...
I think I sent it to my PhD student. I said, watch this minute, she says it's so well. And...
Homework for everyone, yes. Excellent.
Going back to what she said, it's important somehow I learned not to be stressed. I do many things. I go things for the community, I have many responsibilities. I still work in mathematics. But at some moment, I don't know how, I realized that I can only do one thing after the other one. And just, it's important not to be overstressed. Yeah.
Okay.
And I don't know if this is important, but I remember that I had my first PhD student, and I proposed him to do something, and we sent the paper. There was a meeting in Spain. We sent it on Sunday morning. On Sunday night, I remember there was a French professor who had some paper related to this. And then I started trying to find this paper because we don't have access to paper, but somehow I found it, some notes. And I realized that he had been working with us with the same subject, and there was an intersection. And then I got, panic at the first moment. It's my first student, I proposed something, and it was partly done by this professor. So what should I do? And then the following morning, I realized, okay, but it was not exactly the same. We could use what they had done and just construct on this. And we ended having a very nice paper on this. But it was not just exactly the same. Though it was much better than if this hadn't existed before. But the first moment was, what should I do?
I think I agree. Sometimes you feel like somebody has taken something away from you, or been there first. Or it's actually generally there's something to be worked out. And again, the perseverance is an important aspect. Okay, we'll open in a moment, but I just want to reflect for a second also on how possibly the careers that we have had might change in the future. I mean, certainly from my point of view, research has changed, and I'm very much on the pure mathematics side. So certainly that aspect has changed completely in the sense that, for example, we have Google Scholar, we have Marseille.net online, rather than in big books and libraries. Do you know what libraries are? Okay, you still do. Very good. But I mean, it's completely changed in that sense. The question is, will more career structures change? What do you think? I mean, looking back in your own career, what will be probably different to the next generation? Any thoughts? Any predictions?
It's hard to predict. It will certainly change. We've been hearing here many opinions on what AI is doing to our profession and to our lives, right, as human beings. So it's good to find people who are very positive against it. It's not against it, they're very positive for this, and people are just trying to hide the bad part of it. So I think the important thing is to adapt on oneself. So we just need to go with the flow and do the best what we can. It will certainly change, and I hope it will change for the best.
Corinna.
I think what is great to see, which in the community now, even looking at the people that we have here at the forum, is diversity and kind of different facets and ways of doing mathematics. I think we have more diversity in all senses of in the people who do mathematics, and also more ways to approach mathematics, more ways to teach, more ways to inspire people. So I think it's nice to have a young, diverse kind of crowd, and that makes a difference also, and inspiring the next generation. So if students see more different ways of also approaching, and more flexibility in the career, sometimes more everybody.
Thanks. So people are here from all over the world.
Approaching also different ways of doing mathematics. Again, I don't know, we spoke before of mathematics. I spoke about Olympiads and problem solving. So problem solving is one aspect that inspires people, but mathematics is also other things. Socialization, connecting, explaining. I think we have more diverse type of mathematicians. Some who are good at, I don't know, popularizing, explaining, and connecting. So it's also a richness.
I think technology has changed what we do in obvious ways. Yes, first of all, you get instant access to any publication, which has really sped up the process. You get instant access to any colleague anywhere in the world. So the collaboration network has gotten very tight. The whole process has sped up. And now we have AI, which I look forward to seeing how that affects research in mathematics and theoretical computer science. As Sanjeev said yesterday, I think it is a domain in which it's possible for these tools to really help us in what we do. But as I think I mentioned, the problems, the questions are really more important than the solutions. And these systems yet, the more interesting question is how these systems can help us identify the important problems. Mathematics is symbol manipulation, but somehow it's towards something, taste, structure, elegance, I don't know what it is, but this is a very human thing and it's hard to define. This is what is really important in our
You mentioned it in your talk, and it was mentioned here as well, that choosing the problem and what the aesthetics, effectively, of what mathematics can give as well is really quite something that maybe the AI hasn't yet got, or it will have to be guided by human. We'll see. That probably others disagree, and that's okay as well, because I give you now the voice. Other questions from the floor? Any questions to the panelists directly? You can go back to their talks. There are some, I think, yeah? Please introduce yourself, maybe your name and where you're from.
Hi, so my name's Trillian. I'm a student at Deakin University in Australia. And I mean, this is a question for all of you, but particularly Corinna, you had your slide where you were talking about all the different areas you've worked on and a lot of passion in a lot of different areas. So how do you juggle that? How do you prioritize when you're interested in so many different things? And what advice do you have to someone who's starting out who might have a similar challenge?
So about prioritization and
with passion.
different challenges.
Yeah, prioritizing
Anybody
your
want to
passion.
About mathematics or about other? So
In mathematics.
yeah.
Yeah.
Mathematics. Okay, mathematics.
Yeah, I don't know. I think that there are many intermateriality. There is some coherent alignment. It's a bit how to find the right questions. What guides your research? What guides the various aspects? I think there is a kind of a story that you want to tell and you want to explore. And maybe you explore some aspects, you study some examples, you use different tools, but you sometimes are trying to, I don't know, for example, slow chaos, or you want to identify some mechanisms which create chaotic features, and then you start by exploring them in different examples. Sometimes you're sidetracked, you find a new connection, so the path is not always linear, but sometimes you, yeah. But,
So, to some extent, unconsciously, you follow your path. Is that?
I don't know if it's a posteriori, maybe you try to find a storyline which collects and redirects. I think every time you evaluate what is the next step and where do you want to go, but yeah, I don't know. I don't know if it answers your question.
Yeah, no, it does. Thank you.
Okay. Any other questions? Like us?
There's a hand.
That's somebody.
Couldn't probably touch it.
Hello, my name is Sofia. I am from Cuba. I'm a PhD student at University of Havana. And I want to ask to Professor Alicia. I loved your talk right now and about your life story. And so, which advices can you give to people, young people, that is trying to make science from Latin America, in Latin America?
Well, I don't know. I got help from my family, from colleagues, and from international institutions. I'm sure you can get help from international institutions too. Just follow your passion and you will get help. Write to me if I can help in any way. I don't know.
Thank you.
You're welcome.
Oh, that's a question about that. Away. Good catch.
So, Serbian basketball tradition, but it didn't went well in the last Europe champion. Okay, so I would like to thank all you. So I enjoyed your life stories. So may you make short reflection how you choose the problems for your PhD students, and you talked a lot about how you choose problems for yourself, but I know that you have many students, and one day young researchers will also become mentors, and maybe you can briefly reflect on that issue. Thank you.
Good question. How do we choose questions for our students and become mentors?
I tell my students to read the literature, read skeptically, which is to say, don't take anything at face value. Same with AI, trust but verify. Read a paper with skepticism and proactivity. Think about, is this the right way to formulate the question? What other questions might there be? Am I interested in this? Maybe there's some more interesting question that comes out of this. What we really try to do, or what I try to do, is get my students to generate their own questions, because those are the ones that they're really interested in solving. Students come to me and ask, give me a nice problem, right? The nice problems, I've already worked on them so hard that they're still unsolved. Maybe this is not such a good idea. So,
Actually, I'll give you an answer which is meant to multiply the number of answers. Like, you have a number of wishes from the genius in the lamp, and you say, I want to have more wishes. So I think My question is, look for mentors and ask this question to many people. So, okay, we can tell you how, we have these panel discussions joint between ETH and the university, where we invite 2 senior, 2 postdocs, mathematicians to give advice to younger, to PhD students, and they can ask, we have one title, Becoming an Independent Researcher. So how do you start finding your own problems, asking your own questions? Some of the advice is like, yeah, be critical, be curious, ask every time. But so what you can do, maybe many of you can do, you can organize such a thing in your institution. Maybe if you have some senior people, don't be shy, go and ask them advice also on career and mentoring, so, and create more mentoring opportunities. So you can create for yourself by looking at role models for you, around you, and asking them without being shy how to redirect the path in your lives. And maybe organize something at your institution, asking other mathematicians, other computer scientists to share their experiences and advice. Yeah, we can chat more about it concretely, but I think it's... Yeah.
You want to add to that?
The only thing I would add, so for me it was so hard to learn how to pose my own problems, that I would help students so that they can pose their problems. Maybe not the main problem, but that they know that they can pose problems and just follow their curiosity and don't be afraid this will work.
That's possibly the hardest to teach, how to ask the right questions. We're back to the same topic. Okay. And maybe on that note, I should close this session. So thank you very much, Rob, Corinna, Alicia, for interesting conversation. And thank you very much, everybody, for listening to us. Thank you.
Thank you.